All right, so the exam had 10 questions. Your best 6 were graded. I meant most people turned in 6 answers. About half the people turned in more than 6 answers, so they had a little bit of extra padding. So let's go over these. So number one asks to analyze the kinematics of a bullet being fired from a gun. So the barrel of this gun is 25 centimeters, also known as 0.25 meters. And the acceleration is, well, it's big. Right. Our initial velocity when the gun is fired is 0. So we have distance, we have acceleration, we have initial velocity. We want to know final velocity. We're going to say that to the right is the positive direction. And given what we've got and what we know, kinematics number 3 seems like a pretty good bet. Alright, so v final squared is 0 plus 2 times 580,000 times 0.25. So final velocity squared is what? It's 2 times a quarter, so you get a half times 580,000. So that'll give you 290,000. And square root of that is about 540. The most common mistake that I saw here is that instead of converting this length to meters, people just left this as 25 centimeters, which means that your velocity is going to be 10 times too big. I only took off 1 point for that, if you got the rest. All right, questions or comments here? Nathaniel says, I way overthought this one. Yes, that is typical of most people's solutions for most of these problems. How detailed did the drawing need to be? I mean, you saw how bare bones mine was. So I think if you put down literally any drawing, I gave you points for putting a drawing on this one. All right, number 2. We have another one-dimensional kinematics problem, but here we're looking at vertical movement rather than horizontal movement. We have a shot put, which has been thrown straight upwards, which is not the way you want to toss a shot put. It's going to travel up till it reaches some max height, and that's actually all that we're interested in here. So our initial velocity, all right, so we're going to say that up is the positive direction, so that's the positive y direction. Initial velocity is 7.5. Initial height is 2.2. Acceleration is minus 10. That's from gravity. And there were a couple of ways to attack this, but the easiest is if you realize that at the apex, the y velocity will briefly be 0. And so you can solve for everything you need if you've made that that assumption. So we can use perhaps K2 and say V is equal to V naught plus AT, and the velocity will briefly be 0. It started off at 7.5 10t. This tells us that the time is going to be 3/4 of a second. Similarly, we could use K3 to give us the maximum height. If the initial velocity is 0, right, then we have 7.5 squared minus 20 said 20, wrote 10. 7.5 squared is like, I don't know, 55, maybe. 56.25. All right, excellent. So our change in y is something like 2.8. Now, if you just put 2.8, I actually gave you full credit for that. But that's not the actual height of the shot put. That's just how far above its original height it went. And it started at 2.2 meters. So its final height is going to be 5 meters. You could also definitely have done this problem using K1 instead of K3 once you had time, right? You could also have said that your maximum height equals your initial height and that'll also give you about 5. All right. I think for the most, why is it 5? Because you gained 2.8 meters of height during the flight, but you started at 2.2. So you went from 2.2, added another 2.8 meters of height for a total of 5. So again, anybody who put down 2.8 as their final answer, I don't think I even took points off for that, because one step of addition didn't seem like it was worth a point. But generally, people who turned in this question did pretty well. Questions, comments? Love to see the politeness in chat. You don't get that in an engineering class. All right. Question 3. Question 3 people struggled with. I had a lot of people turn in a picture that showed a graphical addition of 3 vectors and how it, which is fine. And you got, if you turned in a graphical solution, you got at least half credit for that. And yes, we are recording. The problem is that the question asked for 3 arbitrary vectors, and if you draw some vectors, what you've actually shown is 3 particular vectors. So what I'm looking for, what I was looking for, is something like, so show that each of these vectors is components. So you remember, we can't actually do effective math on vectors until we've broken them up into components. And that's true whether or not we have numbers to plug in. So if we add A and B first, then A plus B is the vector AX plus BX, AY plus BY. And then we'll add C onto that. And then when we add C, we get AX plus BX plus CX in the X direction, AY plus BY plus CY in the Y direction. If we do the other pair first, then we'll leave A alone for the moment, and B plus C will be the vector BX plus CX, BY plus CY. And then when we add in A, we get so all we did was we used the definition of vector addition, right? So if we want to add vectors, we have to break them into components, which is something that we can always do. And once they're broken into components, the addition of 2 vectors means adding the components. All right. Questions, comments on this one? I mean, everything's easy if you know what the answer is. So okay. Next one. some flight. So this is a purely vector problem. So you fly. So here's our coordinate axes. And let's say you hop on a plane and you do one of these. You fly 28 kilometers, 25, not 30, 25 degrees south of west. So that means, right, and we'll call this vector A. Right, that means that the components of A are 28 cosine 25 and 28 sine 25. Where here, I'm going to go ahead and say that to the left and down are the positive directions. Alright, so we plug in that trigonometry, we get 25.4 and 11.8. So your actual flight was 28 kilometers. If you had flown directly south and then directly west, you would have gone 25.8 kilometers and then 11.8 kilometers. So the distance that you would have traveled would be 37.2 kilometers. Right, considerably longer. Part C then asks, well, what if instead of going directly south and then directly west, what if you started going 45 degrees southwest and then did 45 degrees northwest to reach the same destination? So that's like saying, so there's our original, that's, apparently I am having trouble drawing straight lines today. So here's our original travel itinerary. So what if we went 45 degrees and then made a 90-degree turn and went northwest? Right, so we can call these like maybe B and C. There are a few ways that you could have gone about this. I think the simplest way is to realize that if you're going to take this path, then what we have is that whether you take path A or you take path B plus C, you end up at the same spot. And B, since it's 45 degrees southwest, the components of B are going to be B cosine 45 in the x direction, B sine 45 in the y, and I totally ran out of space. So let's try that again. Yeah, Casey, I can definitely do that. So here's our, so in black is our original x-axis. So our original flight plan was 25 degrees south of west, and our revised flight plan here was 45 degrees south of west. Does that make sense?
I have a question. So, so you showed that both angles were like total 45 for, so would we not need to subtract 45 with 25 to get that angle, like that small angle that B from B?
Yeah, so that's the other way of doing this problem, and I'm going to cover that in a second.
Okay.
So there were two main ways of going about this. I'm going to show this way first, and then we'll show the other way. Um, so with reference to our original coordinates, this black coordinate grid, B is going to have these coordinates, and then C is going to have, right, so C cosine 45, but then its its y component is going to be negative because it's going to be going, so that the C is going up and to the left, and left is the positive x direction, but up is the negative y direction here. Why is that angle 90 degrees? Because the difference between 45 degrees southwest and 45 degrees northwest is 90 degrees. Um, for this method, you don't actually need to know that's a right angle, but for the second method, you will. Okay, so with this broken down, so we now have for this vector equation in orange to be correct, we need the x parts on the left-hand side equal the x parts on the right-hand side, and the y parts also have to be equal on the left-hand side and right-hand side. So we can write 25.4, this is the x part, equals b cosine 45 plus c cosine 45. And in the y direction, we can write 11.8 equals b sine 45 minus c sine 45. Oh, yeah, that should be sine. For this case, it actually doesn't matter because cosine 45 and sine 45 are both radical 2 over 2. But yes, I meant to write sine there. Okay. So we've got we've got a system of two equations here, two equations, two unknowns. We don't know B, we don't know C. So in principle, we can just solve these. I think the easiest way is to realize that cosine 45 and sine 45 are the same. They're both radical 2 over 2. And so if we do the x part minus the y part, we get 25.4 minus 11.8 on the left-hand side. On the right-hand side, we get 2 of these, radical 2 over 2 times b. And then we get c radical 2 over 2 minus c radical 2 over 2. They cancel. Yep. So I actually meant to cancel the other side. The other ones. This should be. So if you subtract, the b's will cancel, the c's will add up. Yep. Sorry, I've only had 1 cup of coffee this morning. So this tells us that c is going to be equal to 9.6. If we do the other thing and we add these two instead of subtracting, the c terms will cancel and the b terms will add up. So we'll end up saying, so this is from subtracting. If we add instead, we'll get 37.2 equals square root of 2 times b. So b is 26. All right. So if you traveled b then c, you would have traveled a total of 35.9 kilometers. There is another way to attack this, but it requires a little cleverness, and I did see a few of you attack it this way. So if there's 25 degrees between the x-axis and our original flight plan, and there's 45 degrees between the x-axis and our new flight plan, then there is 25 degrees between them, which means that this ABC triangle is a right triangle with an angle of 25 degrees, or, yep, 20 degrees. Thank you, Chad. Which means that we can just do some trigonometry on this ABC triangle here. In other words, the length of B is going to be 28 cosine 20, and the length of C will be 28 sine 20. And that's, that's actually a much easier way to do the problem, but it does require a little bit of cleverness, which I try to avoid if I can help it. All right, questions, comments? The green angle is 20 because we can see it's the difference of the orange angle and the blue angle. Or in other words, the blue angle plus the green angle have to add up to the orange angle. All right. Problem 5. We got a quarterback. Quarterback's tossing the ball. At an angle of 35 degrees. This is very similar to a problem I went over in lecture. Yes. Except in lecture, I think it was a place kicker and not a quarterback. Anyway, the long and short of it is one dude throws a ball, second dude catches it. They are separated by 21 meters. The fact that the quarterback was moving straight backwards, that is actually a red herring. That's extra information. It doesn't make any difference. Alright, so we're going to say up and to the right are the positive directions here. And we define our usual vectors. So maybe we start the point where it's thrown is going to be our origin, which means the point where it's caught is going to be 21 meters different in the x direction, but the same height. The initial velocity, we don't know the speed, but we can say that the components of the velocity will be right v naught cosine 35 in the x direction, v naught sine 35 in the y. Our acceleration is just gravity. We don't know time. Okay, so this sounds like a job for kinematics 1. As usual, we're going to break that down into x and y components so that we actually get two equations. And we do have both of our unknowns. The v naught and t are in both of our two equations, but we do have two equations, so in principle, at least, we can do some solving. I'm going to start with the y direction here, because I think in lecture I started with the x direction. So let's start with the y direction. We notice we've got 0 on the left-hand side, and t and t squared on the right-hand side. So we can totally factor out a t. So if we've got two things multiplied together giving us 0, that means that one or the other or both of our factors has to be 0. So it could be that t equals 0, except that's t equals 0. That's the moment when the ball is released, not when it's caught. So that's actually not the solution that we're interested in. So we are interested in the solution where the thing in parentheses is 0. So in other words, when v naught sine 35 is equal to 5t, so v naught is equal to 5t over sine 35. And then we can take that, plug it into the x direction. We get cosine over 35 and a sine 35 here. So that's going to be like a 1 over tangent. So we get 5t squared over tangent 35. And then we can do a little bit of solving. So tangent 35 times 21 over 5, square root of all that will give us time. And that's 1.71 seconds. Take that, plug it back in over in the y direction. And we get v naught equals 14.9. All right, questions or comments? Yeah, so we did part B first. This is not the only way you could have gone about this, but I think this is the most straightforward. What I did see a lot of in this problem is what I like to call magic equation syndrome. Plenty of people wrote down a function for range in terms of sine 2 theta and v naught. Here's the problem. The kinematic equations that we've been using, K1, K2, K3, when is it okay to use those equations? When are they correct? Yeah, they are correct whenever you have constant acceleration, which is everything we're going to consider in this class. So those equations are always correct. This formula for r down here, when is that correct? Yeah, it's projectile motion where the only acceleration is gravity and the object begins and ends at the same height. Now, it turns out that those restrictions do apply in this problem. However, nobody even considered whether or not this was an appropriate formula to use. Right? Nobody made any note of that on the exam. So, if you used this formula with no note, with no mention of anything else, that was minus a point. If you came to office hours, we derived this formula. And the way you get this formula is by using K1 in the x and the y direction. Right? So, under some assumptions. So, this thing for r over here is really just K1 dressed up in different clothes. You don't have to show the derivation. Tests are way too short for that. But you do have to make note, you do have to show me that you know there are restrictions and that you've considered whether this is an appropriate equation to use. Because if you don't, then Right, you're guessing. It does say in the problem they're caught at the same height. But if you don't, if you, I need to see that you've considered that, basically. So if you, right, so like if you're going to use a formula, I need to know that you know it has limitations. That's right. If the ball had been caught at even a slightly different height, this formula would not apply at all. So, of the tests that I've graded so far, nobody considered whether showed that they considered it at all. So that's irksome. But if that was the only thing that was irksome about the problem, then I only took off 1 point out of 6. So, Nathaniel, you say you thought it was applied, and there is an argument to be made there. If I was talking to a colleague, right, I would know that they knew when the equation applied. But since this is the first work that I'm seeing from you, I need you to prove it to me. Like, I need you to show me, right? So, I mean, it is implied, but I don't have any way of knowing if you got the implication unless you put it down on the paper. Does that make sense? Okay. So if there's no explanation, then I'm left wondering, well, did they know that this was a good equation to use, or did they just copy what they found on YouTube? I'm not calling anyone out there. I just know that there are definitely videos on YouTube that have solved similar equations. All right. So even if you put down the equation number from the book, that doesn't tell me that you've considered the limitations of the equation, right? Because this thing down here, this is not always true. But this, always true for this class. It is longer, but it also doesn't obscure the physics of what's going on, right? Like this solution in pink over here, right? We we definitely know what physics are happening here, but the blue one over here, like that's it's not exact. Not only is it, do we not know necessarily where the equation came from or what it's for, but it kind of hides what's going on. So when I am lecturing, I will only start with formulas that are always true. And in fact, maybe when we finish this, going up through here, it would be useful to revisit our toolbox, right? So our toolbox is the the equations that'll always be correct to use. And there's not that many of them. We only have 4. But yeah, we will definitely get there. We'll do that at the end of the test review. All right. Now we're into to forces. We have a ship. Yep, if you forgot to do a part B, and that's true, I think anywhere in this on this test, if you did one part but not another, then I think I took off 2 points for that. Alright, so if we're firing a 1-ton shell, so first of all, 1 metric ton is exactly 1,000 kilograms. So this is an invitation to use Newton's second law here. So we'll go ahead and we'll define the x direction to be whatever direction we're firing the shell in. So then the sum of forces, right? The only force that's really at play here is the force from the ship to the shell. And that's going to equal mass times acceleration, which is 1,000 times 25,000. Right, so 2.5 times 10 to the 4 times 10 to the 3. So that's going to be 2.5 times 10 to the 7. And then by Newton's third law, the force of the ship to the shell is going to be equal and opposite the force from the shell to the ship. And they did say magnitude, so if you, whether or not you put a negative sign on this number, I gave you full points. Okay. Questions or comments here? Yeah, it was just writing the same answer twice. This is correct. And if you did the force from the ship to the shell, and then you just didn't answer the second part, I only took off 1 point. Yeah, if you just put 2.5 times 10 to the 7, that's 5 out of 6. I don't think I even took off for not drawing a picture on this problem. I've specified the direction for the second part, but left it positive. Yeah, that's exactly correct. If your picture was a dot and a line, that is perfectly fine. Okay. Question 7. Tough Mudder. Anyone done this race? It happens in town every year. Well, you two have my respect. I have done an attempt at the Tough Mudder. I did not finish. I did not finish at all. All right. So let's say you've got to do a rope climb. There's a rope, and you're holding on. There we go. Hey, I like that picture. We're going to call up the positive direction. And the forces, so we're going to call up the positive direction. Part A. The forces that we're experiencing here are tension and weight. Actually, that's going to be the same for all parts. Okay. So, sum of forces in the y direction. If you are just hanging there, catching your breath, you are motionless. Sum of forces is going to be 0. So that means the tension is equal to your weight, which is going to be 700 newtons. Part B. If you are steadily climbing the rope, then your acceleration is still 0. So the tension in the rope is the same. And lastly, if you are actually accelerating, then the sum of forces is going to be ma. So that means tension is going to equal ma plus mg. Maybe factor out an m. Why is acceleration still 0? Yeah, so Jolin's got it. So if you're moving, but you're moving at a constant rate, then you're not accelerating.
Oh, like for the B, like how do we know it's at a constant rate? Like it didn't mention it was at a constant rate. Like do we just assume that when it says speed?
Yeah, so I think that's a reasonable assumption. Right? If you're climbing the whole time at a speed of 1.5 meters a second, that means you're not changing your speed, right? Either way, I think I only made part B worth 1 point. So if you missed part B and got everything else fine, that's 5 out of 6. All right. Question 8. Pushing a block of ice across a frozen lake. Most of you got this hint about 12 degrees Celsius, and you looked up the coefficient of friction. For ice on ice at 12 degree at minus 12 degrees, and that's 0.3. It's not in the textbook, but you had the internet. Okay, so our picture looks something like this. Block of ice, frozen lake, and you are pushing down on it like so, with a declination of 15 degrees. You're pushing with some amount of force. The block of ice also has its own weight, its normal force, and its friction. And we'll go ahead and call up and right the positive directions. Alright, so if we're saying up and right are positive, then our forces, our normal force is going to be only in the y direction. Our weight will also be only in the y direction. Our friction will only be in the x direction. And pushing force, we will have to do a little trig on, but we can see it's going to be p cosine 15 and minus p sine 15. Okay. So then we pull out Newton's second law. Sum of forces in the y direction is n minus mg minus p sine 15, and we do expect those to add up to 0. Alright, in the x direction, we get p cosine 15 minus mu n. We also expect that to be equal to 0. And then we can plug in what we got for n from the previous equation. A little bit of algebra, factor out a p. So sum of forces in the x direction is 0 because we're looking at what's the minimum force required to move the block. So we're applying just enough force to equal out the maximum static friction of the block. So from here, it's just a plug and chug, and we get 151 newtons. Yeah, the maximum static frictional force, that's the amount of force you have to apply to get it started. All right, so that is the first situation when we're pushing down on the block. If instead we were able to push up on the block, right, and apply our force like that, then all of our work here would be the same, except the y component of P would be positive, which would mean positive here, which would mean negative here, which would mean negative here, positive here, and thus positive here. So it would only be 129 newtons. All right. Questions or comments?
Wait, what does happen with like the green stuff? Is that if we change the angle?
Yeah, so part B of this question was like, what if instead of pushing down at an angle of 15 degrees, you pushed up at an angle of 15 degrees? And so the green marks are the way that this situation would be different if you were pushing up instead.
Okay, thank you.
And that's done. I only did it that way for in the interest of space here. Um, and again, if you did the first part right, but you missed the second part, that was really only worth a point. All right, we're in the home stretch. Recording still going strong. All right. What is the radius of a curvature of a bobsled turn? Right. So here we have a banked curve question. Right. So our curve is banked at 30 degrees. Here's our bobsled team. They have their own weight. They have normal force. Thank you, Jolyn. Got to the mute button just in time. So here we don't have any friction. So the problem says that there's no friction here. And I'm gonna say that up and to the left are the positive directions on this one. So written this way, our normal force is going to be equal to the little trig, and our weight will all be in the y direction. All right. So our velocity is, in this case, it's going into the screen. So it's in what we might call the z direction. So maybe let's draw a secondary little bird's eye view of what's going on here. So we are here on the curve, and our velocity is, at least momentarily, it's going this way. And this curve has some radius of curvature, which we would actually like to find out. So that said, we turn to Newton's second law. The sum of forces in the y direction, banked at 30 degrees, what does that mean? It just means that it's, right, it's that the angle that the surface of the track makes with the horizontal is 30 degrees. And why do we get to use theta equals 30 degrees for n? Can you clarify your question, Casey?
Sorry, can you guys hear me?
Yeah.
Am I hearable? Okay. So I see that theta there makes that angle. I just don't see how that those two components correlate to n
Okay.
because it's not going in that direction.
So n is going off in this direction. So that's going to be partially in the x direction and partially in the y direction. We have to play a little angle game here. So there's the like larger ramp that we are on. So if this is theta here, it means, alternate interior angles tells us that this is also theta. And then if this is theta, then this angle here has got to be 90 minus theta, because the surface of the ramp and the normal force make a 90-degree angle. And if that's 90 minus theta, then this top angle up here has to be theta. Which that means that the y leg is actually adjacent to theta. So that's why we get n cosine theta for the y direction. Cool. So take sum of forces in the y direction, and we get n cosine theta minus mg. And we dearly hope that this is 0. Otherwise, we're going to have a really really seriously injured bobsled team. So our normal force is going to be mg over cosine theta. if we look at the x direction next, sum of forces in the x direction is just n sine theta, but the sum of those forces, because we're on a circular piece of track, the sum of those forces has to be mv squared over r. So let's take our expression for normal force from the y direction and plug it in here. So we get mg sine theta over cosine theta. Sine theta over cosine theta is, of course, tangent theta. So when we're solving for r, we can multiply both sides by r, and then divide both sides by mg tangent theta. We get r equals mv squared over mg tangent theta. Now, this question had a lot of the same magic equation syndrome as question 5 had, right? Where some people just started by quoting this result, r equals v squared over g tan theta. And for the same reasons, I took off points, right? It obscures the physics that's going on. No consideration was made as to whether this was appropriate, what the restrictions on this equation were, right? It's like Newton's second law is always true. This thing here is a special case. So if you want to use a special case, you have to consider and show that you've considered whether that special case formula applies to this situation. That's right. And if you're just jumping to magic equation, you're also not drawing a picture. You're not breaking down forces. You're not defining your coordinate system. All of that stuff is obscured by the magic formula, and so yeah, you're going to lose a few points for setup.
For the normal force, you drew like all those like angles and like the sine of theta because our coordinates were didn't have like the tilt. It's because they were like straight down and straight to the left.
Yeah, so even though this is a ramp problem, I didn't tilt the coordinate system, mainly because I wanted the centripetal force to be only in the x direction. Does that make sense?
Okay, yeah, thank you.
Yeah, and then the consequence of wanting the centripetal force to be only in the x direction here, consequence of that is that the normal force is not just in the y direction. Any other questions or comments before we move on? Yeah, so if you want to use special case formulas in the future, and you write down what the restrictions on those formulas are, and you consider that they do apply in this case, full points. Yeah, like a checklist, exactly. So like for this formula, the r equals v squared over g tan theta, your requirement is banked curve, circular motion, no friction. All right. Last one. Loop of a roller coaster. Wow, that was terrible. That's better. Yeah, so if you came to office hours, we did a roller coaster problem using work and energy, um, and it ended up being pretty similar to this. So here's our roller coaster cart here. There is weight acting on the roller coaster cart. There is also potentially normal force from the contact with the track. Also, I'm going to go ahead and call down the positive y direction. So normal force always is in the direction of surface to object. So in this case, the surface is above the cart. So since the surface is above the cart, it's got to be pushing down onto the cart. All right, so Newton's second law. Sum of forces in the y direction equals minus, or not minus because down is positive. So N plus mg, and the sum of these forces, if we have a circular bit of track that we're on, some of these forces has to be mv squared over r. Okay. When we're looking for the minimum speed, right? So if we look on the left-hand side, if the left-hand side gets smaller, then the speed required on the right-hand side also gets smaller. The weight of the cart cannot change, so that's fixed. However, the normal force could potentially decrease. So, in fact, if we came around the loop-de-loop and we were just barely making contact with the track, then the normal force would essentially go to 0. It would be a scary experience, but it could happen. And if it went to 0, then we would just have mg equals mv squared over r. Masses cancel. And square root of gr is your minimum velocity. So g is about 10, r is 12, 10 times 12 is 120, 120 is about 121, square root of 121 is 11. So yeah, so if that's right, William, if we're considering the minimal speed, then the normal force has to be 0, because that's as small as we can make the left-hand side, is normal force being 0. If you didn't list it, then that's fine. All right. Questions or comments on this last one here? All right. Let's take 10. It is currently 9:58 by my clock. Let's be back here at 10:08 to talk about work and energy.